Hello, physical geology enthusiasts. Here we are for episode 4, talking about rocks and the rock cycle. And this lecture is powered to you by Sugar-Free Red Bull. So grab your caffeinated beverages and let's get started. So where we were in our last episode was talking about minerals. And what we said about minerals was that they are a foundational concept of both physical and historical geology. And that's because they're the building blocks of really our continental crust and our oceanic crust. And that's really going to play into bigger ideas of mountain building and plate tectonics when we get there. So with minerals, what we said is that they're identified by 3 physical properties. We said that minerals are those that are naturally occurring, that they have a specific chemical composition, and that they have crystallinity. And so those are foundational concepts of what defines a mineral. We also said that we can separate minerals into silicates and non-silicates. And so the most abundant minerals that are found on the Earth's surface include silicon, oxygen, and aluminum. And so that makes sense that the silicates that have the root of the chemical composition SiO2 is most abundant on the Earth's surface. So 90% of all minerals found on the planet are going to be considered silicates. And then you have non-silicates, and that's really everything else. So non-silicates are those minerals that can stand alone and are singular elements. So we talked about sulfur, copper, zinc, lead, boron. Those are independent, standalone elements. So any of like our heavy metals are considered to be non-silicates. But the majority of what we find on the planet is going to be silicates. The most common silicate and the purest silicate, SiO2, is quartz. And so we find that in abundance all over the planet and close to the Earth's surface too. So then the last thing that we discussed was how do you identify a mineral, and we use specific characteristics and means of identifying minerals. So we talked about the color, the streak, the hardness of a mineral, the cleavage of a mineral. And another thing that we can use specifically to like calcite is its reaction to acid. There's a mineral that's called magnetite, and it has a magnetic property. So there's some individual specific tools that we can use to separate and identify minerals. But here we are today. We've moved forward, and we started to talk about rocks and the rock cycle. And what we need to recognize is that all rocks are made of minerals. So minerals are the key components of rocks. So in general, we can think of one that's pretty common, granite, right? We use it for countertops. Granite is a type of igneous rock, and it contains quartz, a biotite, and a feldspar. And the different amounts of those minerals will give it a different types of appearance, right? So if you've ever been to Lowe's or Home Depot and you've looked at the granite section, which I get really excited about, you can see all different types of varieties of different types of granite. And so it's just those variabilities in color and uniqueness that gives them differences in appearance. So minerals form rocks. And so that's why we started last week talking about minerals. Now we're talking about rocks and the rock cycle. So I've identified the rock cycle. You can see it on the PowerPoint. There's 3 main groups of rocks that we'll explore. That's igneous rocks, sedimentary rocks, and metamorphic rocks. And we call it a rock cycle, but truly, if there's a start to the rock cycle, we're going to start with that body of magma that generates in the outer core. So you have the inner core, the outer core, the mantle, and then the crust. And so that outer core is still under pressure to the point where those minerals are in a liquid substance below the surface that's called magma. So as that magma works its way up to the Earth's surface, it's going to solidify as an igneous rock. So the main process involved with igneous rocks is solidification of the magma. If that igneous rock is exposed at the Earth's surface to weathering and erosion, it will break down to sediment to form a sedimentary rock and go through a process of compaction or lithification. And then that sedimentary rock can undergo heat and pressure to form a metamorphic rock through the process of metamorphism. If a metamorphic rock is exposed at the surface and eroded, it can break down to a sedimentary rock. If it undergoes heat to the point where it melts, it becomes an igneous rock. So we can move around the rock cycle, and it's actually quite complex, especially when you get into areas of mountain building, like the Appalachian Mountains or the Rocky Mountains, part of the North American Cordilleran. So what we mentioned before was it's really exciting to study rocks because they give you an understanding of what has happened in the past. And so remember, we're dealing with 4.6 billion years of geologic time. So thinking of how these rocks have formed at the Earth's surface and how they've changed over time gives us clues as to what has happened in the past. And for me, that's life. That's so exciting. I want to take you on a journey quickly through this rock cycle. So I want to talk about some specifics of igneous, sedimentary, and metamorphic rocks. This is a brief overview. If you are totally jazzed by this, then you should take my physical geology class because I really get into the nitty-gritty much more. And then if that jazzes you up, then you should take a class that's called geomorphology, and that has to do with landscape evolution over time. So we really focus on plate tectonics, mountain building, and the story that these rocks have to tell. Okay, so let's get started with igneous rocks because that makes sense based on our rock cycle. And we learned that that igneous rocks formed by the solidification of magma. So my question for you is, when do you see magma at the Earth's surface? When do you see magma exposed on the Earth's surface? And this should be an obvious answer because you should want to talk about volcanism and volcanoes. Gosh, and who doesn't love a good natural disaster? So let's introduce the last major volcanic episode that has happened in the United States. And this is probably way before you were born, but the last eruption in the United States occurred on May 18th, 1980, and that was the eruption of Mount St. Helens. If you've ever been or aspire to go to the West Coast, specifically the state of Washington or Oregon, there is a mountain range that's called the Cascades. And within the Cascades, there are 7 volcanoes that are called the Seven Sisters. And so it includes Mount St. Helens, Mount Rainier, Mount Baker, Mount Hood, and there's 3 other ones that are less common, but they're part of the Seven Sisters. And these are still all active volcanoes within the United States. So they still have the potential to go through eruption. We talked about recurrence intervals. Usually when we talk about recurrence intervals relating to volcanoes, we term that repose, R-E-P-O-S-E. The repose of a volcano is its recurrence interval. So Mount St. Helens is likely on a 50-year recurrence interval, and for that reason, we've started to see activity. It was super active in 2019. We expect it to be maybe even more active in 2020. So Mount St. Helens erupted on May 18th, 1980, and it's a really great story about citizen science. So a month before Mount St. Helens erupted in April, the seismometers, so when that body of magma is moving its way up to the surface, like it's cracking and shaking the earth, so you get seismic activity, like you get these little earthquake tremors. So we can measure that, right? It's energy, so we can measure the release of energy. And the geologists out in Washington State reported that. And so they're like, we we think that Mount St. Helens is going to erupt. We think we should evacuate. And so they evacuated the area, and the volcano didn't erupt. So it kind of made the USGS look a little silly, because it takes time, energy, and money to evacuate people. And people get scared. The good news is that in this area of Washington State, it's not so populated. So there wasn't a whole lot of people to move, but still, people had to for sure leave their houses, or were encouraged to do so. So May 15th comes along about a month later, and the USGS is like, we should evacuate. We need to evacuate these people. Mount St. Helens going to erupt. And the people there were like, we did this before. We don't believe you, basically. And so the majority of the people stayed, and then there was an eruption. So that's tricky when we're trying to communicate science, and we've definitely, in my field, learned from that. But it's something that we constantly have to deal with, right? So May 18th, 1980, the volcano erupted. And that was the last time that there was a major eruption within the United States. But we're constantly looking at that. So in the form of igneous rocks, we have a really good understanding of how they form and how they solidify, because we can see that process in modern day at the surface. So this is like the present is the key to the past in real life. So volcanic activity brings the magma to the surface. And when we talk about igneous rocks, we really want to focus on the solidification of those individual minerals. So I just want to introduce something very quickly called the Bowen's reaction series. So what you're looking at is the names of minerals that you should be pretty familiar with from lecture and from lab. And I'm going to write this inverse, because truly Bowen's reaction series should look like an inverse Y, where quartz is up here at the top, and the temperature that relates to quartz is 800 degrees C, and we'll put 1400 degrees C down here at the bottom. So if you could rewrite that in your notes to look like an inverse Y. And the reason why I like to do that is because we're considering a body of magma that's below the surface moving its way up towards the top. So naturally, if that body of magma is at depth, it's going to be hotter. So 1400 degrees C moving up towards the surface, it's going to begin to cool to 800 degrees C. So what Bowen's reaction series is telling us is it's telling us how minerals crystallize out of a body of magma. How minerals crystallize out of a body of magma. So let's just think a little bit more about that, whereby we have a surface, and let's just say we have a body of magma. And within that body of magma, we can have any mineral or element on the periodic table, right? So you can have calcium. We said in our last lecture that silica and oxygen are the most abundant. You can have iron, magnesium, copper. Those are non-silicates in your body of magma. So you have all these elements in that body of magma, and as it's moving up towards the surface, what's happening is that specific minerals are crystallizing out of that body of magma at specific temperatures. So when we look at Bowen's reaction series, at 1400 degrees C, olivine crystallizes. As that body moves up further, at 1300 degrees, you have pyroxene. At 1200 degrees, you have amphibole. At 1100 degrees, you have biotite. So what Bowen's reaction series is describing is the specific temperatures at which minerals crystallize. And that's fascinating. So if I'm a geologist and I find a piece of olivine in situ, in place, like I'm hiking along and I see an outcrop and I find a piece of olivine, I know at what temperature that body of magma was. And that's exciting. That's part of the story, right? 1400 degrees to crystallize. What's interesting also about Bowen's reaction series is it tells us the journey of that magma all the way to the surface. So by the time that magma cools to 800 degrees C, everything has crystallized. And the last thing to crystallize out of that body of magma is quartz. And so that makes sense, right? Because we said that the chemical composition of quartz is SiO2, and that's all that remains. It's the last thing to crystallize out of that body of magma because everything else is gone. All the other elements have already crystallized. How cool is that? And so that's why you can find quartz all over the planet and close to the surface, because the body of magma has approached the surface and it has crystallized. There's two other terms on Bowen's reaction series, and that is the term mafic and felsic. Mafic and felsic. And so minerals that are felsic contain greater than 50% silica. Greater than 50% silica. Those that are mafic contain less than 50% silica. Okay, so this makes sense when we look at Bowen's reaction series, because quartz has a chemical composition of SiO2, and it's pure. It's a pure silicate. It's the most pure silicate, right? All that forms it is silica and oxygen. We're going to come back to those terms because they're going to be important. So, moral of the story is that Bowen's reaction series gives us a glimpse as to how igneous rocks form and at what temperature they form. So, as an example, again, if we look at Bowen's reaction series, granite is a type of igneous rock. And that's, you can see it all over in your tabletops. If you've ever been to Sioux Falls, South Dakota, you can see this fantastic pink granite. And granite always contains, look at your Bowen's reaction series as I talk, it always contains quartz, orthoclase, which is another name for feldspar, orthoclase, and biotite. So a granite then is going to form between 1100 degrees C and 800 degrees C. And when we talk about granite, like as a generality, we say that granite forms continental crust. So the crust that we find under the surface of our feet is granitic. Like our bedrock of our earth is granitic. And so that means that it cooled 4.6 billion years ago between 1100 degrees and 800 degrees C. So knowing the melting and crystallization temperatures is really useful if we're trying to interpret landscapes. Now there's other terms that we use to describe igneous rocks. And those terms are extrusive and intrusive. So something that is extrusive has exited the surface of the earth. And so that means that we're thinking about volcanoes, right? So that magma has exited the surface of the earth. It's met the atmosphere, and so it cools quickly. So it instantly cools when it comes into contact with the environment, the oxygen, right? Or you can have an igneous rock that forms intrusively below the Earth's surface. And so just like granite, so you're imagining that body of magma working its way up to the surface, it's cooling as it does so, and so it is solidifying underground. And so when you think of a piece of granite, you can look at those large clasts to identify the different types of minerals. So when we look at these in lab, we're going to use specific terms to identify igneous rocks. So the terms that we used to identify minerals, those are just for minerals. These terms are just for igneous rocks. So we are going to ask the question, if the rock solidified underground or at the surface first. So we're going to ask if it's extrusive or if it's intrusive. And in order to answer that question, we have to look at the grain size of those individual minerals. We have to look at the grain size of those individual minerals. And so that provides us with something that's called the texture of the igneous rock. So those that are extrusive, the magma solidifies quickly, and so that texture is called aphanitic. It has an aphanitic texture, which means that those individual, I'm going to put this up so you can spell that, which means those individual grains are going to be small. They're going to be small grains that are less than 1 millimeter in size. And this will make more sense when we start to physically look at igneous rocks. Those that are intrusive have a texture that's called phaneritic texture, and that is large grains greater than 1 millimeter. And again, these terms are just used for igneous rocks. Phaneritic and aphanitic. So with the phaneritic rock that forms intrusively, like a granite, you can see the large grains, and those large grains might be different colors to represent the different types of minerals. So, so that leads us to a question: which type of igneous rock would be more helpful in describing the environment at the time of its formation? And this really kind of leads us into historical geology concepts. Which type of igneous rock would be more helpful in describing the environment at the time of its formation? So would that be an extrusive igneous rock or an intrusive igneous rock? And so what I'm trying to get you to think of is age. So if you find an igneous rock at the surface and you want to date it, absolutely. So you want to get a specific age for that rock. Should you look for an extrusive rock or an intrusive rock? And the answer, of course, is going to be extrusive, because as soon as that magma comes to the surface, it solidifies quickly. And that's going to trap the date of that rock. Not to say that you can't age date an intrusive rock, because you certainly can, but you have to realize that each of those grains are solidifying slowly. And so the age of solidification might be longer. So you can have an age, but you might have an age range. And that will be important when we start to talk about dating techniques specific to absolute and dating techniques, isotopes, the invention of the mass spectrometer, etc. So with specifics to igneous rocks, I just want to introduce some features because it's interesting as you travel and you look at different landscapes. It will make the geology come to life for you, and hopefully you remember this well beyond the class. So we can talk about dikes and sills. Look at the picture with the lady geologist that's in the red. Notice she has a fanny pack on, like she's way before her time. This picture was probably taken in 2000. At any rate, the vertical feature is called a dike. And so what you're imagining is that you have a bedrock, that bedrock fractures, and the body of magma intrudes into that fracture. So if you're ever heading towards Atlanta on 75, you pass the Kennesaw exit, you look to the left, you'll see an outcrop that has all these quartz dikes moving through it. So then if you can identify the rock or the mineral that's in that dike, you know the temperature at which that magma had to be at that area when that solidified. And then the horizontal version of that is called a sill. So you have dikes and sills, and those are both intrusive igneous features. And then, exciting, we can have extrusive igneous feature, right? Who doesn't love a good volcano? One of my very favorite things to do when I travel is to hike volcanoes. So, of course, I've been many a volcano in Iceland, but my favorite volcano all time is Mount Fuji-san in Japan. And if you ever get a chance to visit Japan, it is remarkable. It's a remarkable volcano for so many reasons. It's beautiful, but in the Japanese culture, Mount Fuji is revered. It's revered and is holy, and everybody's supposed to hike Mount Fuji once in their life, only one time. And so when you go there, there's a bunch of elderly people, and it's not an easy volcano to hike by any means. It's not like there's a path. So you're kind of like bouldering up the side of this volcano. And what's also interesting is you start the pilgrimage at night. So you start at the base at about 8 o'clock at night, and the goal is to make it to the summit at sunrise. So it's an intense hike. You're hiking the whole time. But the other thing about it, because it is a pilgrimage, it's completely silent. And so you're hiking 2 by 2, and there's thousands of people on the slope of this volcano, and it's completely quiet. And then when the sun rises, everybody cheers. So volcanoes are near and dear to my heart, is the moral of that story. Here we're looking at explosive features. So common when you see CNN and they're showing a volcano, they often show an ash cloud. And so you can have ash clouds. And then often what happens when you have a volcano that has a lot of ash, that ash is pure silica, mind you, and it can give off static electricity, and it can generate a thunderstorm. And so you end up getting rainfall, and so you can end up having pyroclastic flows that happen. Additionally, if you have a volcano that's covered in a glacier, like Mount Rainier or Mount Fuji, that body of magma comes up, erupts, and then all that ice that's on the surface melts. And so you end up with this terrible flood event that's called a Jokaloop. It's an Icelandic word. And I'm sure I slaughtered that Icelandic word, but it's okay. So you end up with a flood. You end up with a flood event because the ice meets the hot magma, and it can be very devastating. So you have pyroclastic flows, you have ash clouds, and then in non-explosive events, you can have magma that gently flows at the Earth's surface. So this is like a scenario where you have a Hawaiian island event. And so the features that you end up with are called A'a and Pahoehoe. Let me write those down. And those are Hawaiian terms originating in the Hawaiian language. So you have A'a and Pahoehoe. So if you ever get the chance to go to Hawaii, which I hope you do, you'll be walking on volcanic islands, and those features, is when the magma at the surface is jagged, and so you're walking on it, and you're like, and then Pahoehoe is these beautiful, like, ropey features that you can see in the landscape. So with igneous rocks, then, we can talk an awful lot about extrusive features like volcanoes, and I show this diagram here because I ask you, what's the difference between these two volcanic events? So you've got a volcanic event on the right, you've got a volcanic event on the left. And what's the difference between the two? And so on what would be, I'm not sure if this is your right or left, but the side that has the ash cloud is an explosive eruption. The opposite side, where you see the orange magma, is a non-explosive eruption. So the eruption types are completely different. And the reason why the eruption types are different goes back to Bowen's reaction series. And so when you have a felsic-rich body of magma that's close to the surface, you end up with an explosive eruption. So when you have a high amount of silica, that body of magma has a high resistance to flow. That's called viscosity. So it has a high viscosity. And so that magma is trying to work its way up to the surface. And as it does so slowly, it's trapping gases. Then eventually you have a major eruption occur. And so that's what you see anytime you see an ash cloud, it's an explosive eruption. So your biggest and baddest volcanoes on Earth are going to have silica as a primary component of the magma. So we're talking Krakatoa, Mount Fuji, Hekla in Iceland, Katla in Iceland, Mount Vesuvius in Italy. So the baddest eruptions are usually those with silica rich. And you'll know that because anytime there is a light colored ash cloud, it has a high amount of silica. So felsic minerals are going to be gray or white in color. Oppositely, those that are mafic are going to have low amounts of silica. That means they have a lesser resistance to flow or a lower viscosity. And so if you're ever in the Hawaiian Islands, you can take a tour of an erupting volcano and watch that magma slowly move down. And it's quite beautiful, but you're not in danger. Just can't get too close because it will get hot. So that's kind of the introduction and the background of igneous rocks. I mean, I could talk about them for days. You can read more in my Iceland geology textbook if you like. So moving forward from igneous rocks, we can move into sedimentary rocks. And so the main process is called lithification. But before we get to lithification, we have to be able to generate sediment. So any rock that's exposed at the Earth's surface can be broken down into smaller and smaller parts by three major modes. It can be broken down by wind, by water, or by glacial activity. And if we make comparisons between those three systems, ice has the most destructive property, considering all things equal. So we talked about catastrophic versus non-catastrophic events. Of course, catastrophic events like a flood is going to have a whole lot of energy compared to a rainfall event. But generally speaking, when we think of ice, it is the most devastating to a landscape. So you can physically and chemically break down a rock. So physically is the mechanical breakdown. Chemical weathering involves like the dissolution. So we said that rocks are made of minerals. There's a sedimentary rock called limestone, which we're really familiar with in this part of Georgia, and particular to our campus. So you have limestone. Limestone has calcium carbonate, calcium Ca carbonate CO3, and it will dissolve even under rainfall conditions, because you may know that rain is naturally acidic. So rainwater typically has an acidity of 6.7, a pH of 6.7, 7 being neutral, and it is slightly acidic, and so it physically can break down the rock. And that's one of the reasons why you have sinkholes in limestone, which is also called karst topography. So chemically and physically breaking down the rocks into smaller pieces is a major product of a sedimentary rock. And I put this up to show you that sedimentary rocks that are clastic, and we can break up sedimentary rocks into three major categories. We can call them clastic, bioclastic, or chemical. I'll let you write those down. Plastic, bioclastic, or chemical. And those that are clastic are going to be composed of individual grains of sediment. And so you can see on this chart that those individual grains of sediment can range in size. So you might have heard of a sedimentary rock called sandstone. And so sandstone is made of sand-sized particles that are cemented together. Those that are bioclastic are made of individual pieces of shells. So you can imagine walking on the beach and you're walking in that swash zone where there's shells and it hurts your feet to walk, right? You got to wear shoes. That can eventually get cemented together, and that forms a sedimentary rock called coquina. So if you've ever been to Fort Augustine in Florida, that whole fort is made out of coquina because it was abundant in that area. And that's the most rigorous of forts because it can easily break apart. And then the last part is called chemical. And chemical types of rocks are less abundant. But what can happen is if you have the mineral salt at the surface, so if you're ever out in Utah, there is a salt flat from the ancient Lake Bonneville. And that salt gets exposed at the Earth's surface. And usually in desert type, hot type of environments, you might get a little rainstorm. And as soon as the rain hits the salt that's exposed, it evaporates. And so what happens is you end up with what's called rock salt. And so it has introduced impurities through that evaporation process. So like in Michigan, on the roads, they use rock salt to help reduce the freezing point instead of using something that's pure like we eat. So clastic, bioclastic, and chemical, the moral of the story is that lithification is part of that process where you have the cementation of those grains. So individual grains of sediment or shell hash, and they get cemented and compacted together. I show you a picture of the Grand Canyon. Hopefully you'll make it there or have made it there. And sedimentary rocks for days. So you see layers and layers of sandstone and layers of fossils. We'll dive deep into the geology of the Grand Canyon because it's pretty rich in geologic history. If you walk to the bottom, you're in a 3.8 billion year old gneiss at the bottom. So that's the quick sedimentary rocks. We're going to talk in depth about sedimentary structures and environments of deposition. So we're going to come back to sedimentary rocks and tease that out. I just want to give you a little bit of an overview today. And we'll wrap up this lecture talking a little bit about metamorphic rocks. So if you have an igneous rock or a sedimentary rock and you add heat or pressure, it can turn into a metamorphic rock. So the key with metamorphic rocks is that you have to have a pre-existing rock. So you have to have a rock in order to add heat and pressure to. And this pre-existing rock is called a protolith. The pre-existing rock is called a protolith. Let's write that down. A pre-existing rock. So your pre-existing igneous rock or your pre-existing sedimentary rock, you add heat and you add pressure, and that is the process of metamorphism. So people like to say that metamorphism turns ugly rocks into those that are beautiful, because usually what happens is you get secondary minerals precipitate. So you get like garnets or rubies or emeralds that precipitate in the process. But largely, you don't change the composition of the metamorphic rock. So if you start with a sedimentary rock and it's a sandstone, you add heat and pressure, it turns into a metamorphic version called quartzite. So it's more dense than the original sedimentary rock, as an example. If you have limestone, which is a sedimentary type of rock, you add heat to it, you bake it, essentially, it turns into marble. If you have granite, which is an intrusive igneous rock, and you add heat or pressure, it turns into a metamorphic version called gneiss. G-N-E-I-S-S, as in have a nice day. When we talk about the classification of metamorphic rocks, we usually use the terms foliated versus non-foliated, foliated texture versus non-foliated. Foliated versus non-foliated. And when something is foliated, it's banded. It's banded. So you're looking for these parallel layers, and that's because the rocks have undergone such intense pressure that they end up in these parallel bands. So gneiss is an example of that. Schist is an example of that. Phyllite, there's a lot that we'll look at in the laboratory. So this has to do with pressure. Foliation has to do with pressure as a primary process of metamorphism. And those that are non-foliated, the texture is crystalline. And this has to do with heat. So non-foliated, the primary process of metamorphism is heat. And the remaining texture, after you apply that heat, is crystalline. So marble is an example of a non-foliated metamorphic rock that originated as limestone. Anytime that you're out and about and you see rocks that are folded, usually they have undergone metamorphism. In the state of Georgia, there's no way for me to read. Oh, hold on. There we go. In the state of Georgia, we talked about the different physiographic regions of the state, where you have the Appalachian Plateau, the Ridge and Valley, where Berry College is, the Blue Ridge, the Piedmont, and the Coastal Plain. When we look at those different physiographic regions, they have undergone different type of processes. So if you look at the line that separates the Ridge and Valley, the Blue Ridge from the Piedmont, that was the collisional point of Africa 300 million years ago in the formation of the last Pangea cycle. So you can imagine that, like, our state of Georgia wasn't even completely formed yet, right? And so you have Africa cruising across the ocean. It collides with our eastern seaboard to form a supercontinent. It hangs out for a little while, and then it separates by a divergent plate boundary. So that point of collision is the Blue Ridge. And so that's why when you look at the rocks going up through the Smoky Mountains, so up towards North Carolina, where some of the major peaks of the Blue Ridge are, you notice that the rocks are all metamorphic, and that's because they've undergone such intense pressure from the metamorphic process. All right, so I think I will end here today. You've been a wonderful audience. Thank you for your attention. We will identify igneous, sedimentary, and metamorphic rocks in laboratory, so we'll use all these terms that I've dished out to you today. I know it was heavy on the terminology, but we'll get through it and we'll use it. So hopefully you're seeing how this class is building and building into this fantastic body of knowledge. So have a great day, everybody. Stay tuned for more.